Good afternoon, everyone. We'll spend a little bit of time, I guess 14 minutes, talking about, from a MISO perspective, so I'll talk a little bit about MISO as well, how we've been able to kind of navigate renewable integration within our footprint. Our time frame was slightly different. We started getting inundated with wind and solar, well, actually, mostly wind initially, requests back in 2007, and then over the last 10 years or so, we've seen a sea change in a lot of the processes that we employ, both on the transmission planning side as well as system operations. So this will be a brief overview of that, and then the intent is anything that's presented here, if it's useful or can be leveraged in the Indian context, then we're happy to talk about that a little bit more. And as Alan said in his first presentation, of course, renewable sources are not only just creating problems, they're presenting solutions as well, lots of opportunities. And you can see here, invariably, everything that renewables touch, most of the processes, a lot of the tools have been improved from a MISO standpoint to reliably and efficiently interconnect renewable sources. I didn't talk about myself, so I'm Durgesh Manjure. I've been with MISO for about 13 years. Spent a lot of time in transmission planning earlier on with generation interconnection. I was actually responsible for that when we started getting these renewable requests for interconnection. And then over the last few years, I've moved on to real-time system operations. So I get to operate the wind farms that I studied as a planner about 10 years ago. So with that, okay. A little bit about MISO, one of the bigger ISOs in the North American context as well as across the world. Our gross annual charges are about a $25 billion market that we run. It spans about 15 states within the US, and then we have a Canadian province as well. Generation capacity, not as much as what we have here in India, but it's still large by any means, about 190,000 megawatts of generation within our footprint. Peak load, which we've seen so far, it's a summer peaking footprint, about 130 or close to 131 gigawatts of peak load is what we've been able to manage so far. Wind is growing steadily. So far, we have about 16,000 megawatts installed with an instantaneous peak that we saw just earlier this year. It was in April, I believe, close to 14,000 megawatts of peak wind. So clearly, we've been blessed with, we as in our footprint has been blessed with a renewable resource. You can see the wind resource on the left and then the solar resource on the right. So initially, of course, the wind resource is much better than what we have in terms of solar. And as you can see, installed wind is close to 16,000, about a couple thousand megawatts being constructed as we speak. And then the interconnection queue is currently starting about 31,000 megawatts. And solar, we are just getting started. We've installed only a couple hundred megawatts so far, but in study, we have about 16,000 megawatts. So mostly driven by policies back in 2007, almost all of our states came up with renewable portfolio standards, either mandating wind and solar development or requiring it was like a goal. It was not really a mandate, but that spurred a lot of the development on the resource side. And then this slide kind of, I like this slide how it summarizes what we've been required to do, so to speak, to reliably and efficiently integrate renewables. So the first three steps that you see in blue on the left side, those are all the transmission planning related processes or work that we've been doing, and then how it transitions into operations, and then how we've been able to kind of modify or enhance some of our market mechanism to reliably interconnect or integrate wind. So everything starts, at least from a MISO perspective, with an interconnection request. So there's a proposal to interconnect new generation, and in this context, it would be a renewable resource such as wind. And then it's a federally mandated tariff for the Federal Electric Regulatory Commission. There's a tariff that MISO has that we have to follow, and we'll talk a little bit about that, how we've been able to modify that. So that it follows those processes, lots of studies and planning and both engineering studies. The tool that Vikas was talking about earlier. We have some of those tools that we've already been using to kind of screen some of the requests that come in to get an estimate of what sort of transmission investment is going to be necessary to interconnect the wind. And a lot of the times when the developer sees the transmission bill, they have kind of withdrawn from the queue because talked about it at length yesterday as well, that the grid needs to be expanded to be reliably accommodate all of this wind. And we see that, we've seen that for the last several years, and we'll talk a little bit about that as we go. So once all of those studies are done, the stipulations on the service are basically documented in what we call a generation interconnection agreement. Again, it's a federally approved agreement. It's a three-party between the developer, then MISO as the transmission provider, and then the transmission owner, where the generation resource is interconnecting. So once all of that process is done, it is still kind of in the planning realm. So after that interconnection agreement is signed, it obligates the developer to build the facility, the generating facility, and it obligates MISO to provide that service. So then we transition into the operations side. We start collecting modeling data, and I forget which presentation, but maybe earlier in the earlier session this morning, it always takes much longer to build transmission compared to the renewable resource. You can build a wind farm in 12 to 18 months. However, I think it looks like the Indian estimate was about 3 to 4 years to build a high voltage line. In Minnesota, it's even worse. It takes us 7 years from approval, from regulatory approval to building. It takes 7 years to build a line. So invariably, we end up with a lot of generation on our system without having the necessary transmission being built. So that presents a lot of challenges to us in operations, because clearly we know the system's deficient, and we struggled quite a bit earlier on to manage that. Graphical representation of our process, recognizing the time, I'll kind of go through quickly, but the point I would like to make is, and as Mr. Suni was saying yesterday, it's about flexibility. Our original process was first come, first serve. So whoever got in the line first was the one that was being studied first, and then everyone else, no matter how ready they were, had to wait. So what we did with the tariff reform was, if we find that the request is ready to be reliably accommodated and the transmission system is ready. So when I said the request is ready, not just to put in a request in the queue, not just to get in the queue, but they have all the air permits, they have all the regulatory approvals, they have the financing done, and they're ready to build the project, then they get priority. So it's not just about how ready you are to put in a request, it's how ready are you to actually build the generating facility. And also, if you locate it on the transmission system where there is sufficient transmission capacity, you get priority in the queue. So this was quite a successful reform. This was back in 2008, actually August 25th of 2008 when FERC approved it. And that has helped us quite a bit in moving renewable resources ahead in our footprint. There was also talk yesterday, as the penetration increases, I think it was phase 1, 2, 3, and 4 that was talked about yesterday. And the recommendation there was, you need to consider the problem holistically. And that's exactly what we've been able to do at MISO, or I should say we've been kind of driven to do that because of the tremendous volume of wind requests that we've received, that identifying transmission improvements for individual requests would have been extremely time-consuming, would have been inefficient, and transmission is lumpy. You can never right-size transmission. So it always ended up being, so I'm going to build this large line, I'm going to pay for it myself, but then somebody else is going to use it as well. So why don't they pay? So having fair transmission processes, transmission planning processes, along with an equitable cost allocation approach was crucial. And all of this has been developed in the last 10 years or so, and primarily driven by renewable generation. So we do have both an economic assessment as well as a reliability assessment that talk to each other during the transmission planning process. So once the transmission plan comes out of the study work, we know that A, it's reliable to accommodate the generation, and it's efficient as well in terms of economics. So moving on to operations, the chart there you see all the green bars are the actual wind that you can see, or that has actually been installed up to 16 gigawatts, and then the blue bars are projected based on what's in our queue. But the ramp up was pretty rapid. It's almost grew 400% between 2007 and 2011. Our system operators had no prior experience in handling wind. the variability of how much the injection is going to be, at what point of time it's going to be. So maybe it's a little harsh, but I think we were primarily driving blind. We really didn't have a lot of good understanding of how the system would behave with so much wind on our system. So, and there was also the original market design. A variable resource couldn't offer into the market like any other resource. So there was no price transparency. There was no economic dispatch available. So our overall dispatch was suboptimal. It was causing us more congestion costs in the market. And of course, the system reliability was maintained. But then the question started to be, okay, you are reliable. Instead of being reliable, how much is it costing us to be reliable? So that spurred a lot of development on the market side. And the primary solution that we were able to come up with was to make any variable resource behave operationally exactly like a traditional dispatchable resource. In fact, the market product that we came up with is called a dispatchable intermittent resource. So what that actually allows us to do is we actually send a target dispatch or target megawatt output even to the wind farms, just like we send it to a coal generation or a gas generation. And then the wind farm actually obeys that as well. The only difference between the operation, as you can see on those two red blocks there, is currently in our market design, renewable resource, variable resources aren't allowed to offer into the reserves market. They can, of course, offer into the energy market. And then the maximum limit that they can offer in is based on a forecast. It's not based on a nameplate rating as it would be for a combustion turbine or any other traditional resource. But since this inception, this was back in 2011, the life of our operators has improved a lot. A lot of the communication is electronic. It goes through ICCP or interconnection, inter-control center communication protocol. So a lot of the manual work that our operators were doing before this has gone down. There are still some that are still qualified as intermittent resources. They're not quite dispatchable, so that we have to deal with. But majority of the new wind farms are all DIRs, and it has greatly enhanced multiple things like congestion management, unit commitment, price transparency. There's very few negative pricing instances now because we have a good handle on how we manage wind in our market. Recognizing the kind. So of course, this technology relies very heavily on accurate forecasts, and we've contracted out to a vendor in Germany for our forecast, and which uses numerical weather prediction models and multiple inputs. So you can see the black line, which is the combination of all the other traces, and how it closely matches the actual wind output, which is in gray. So our accuracy of the forecast has been improving. Close to 93% or even more on the day, on the actual day or the 4-hour forecast. So the last two slides, I think I would illustrate the point or the benefit of the DIR. So before the DIR, what we were doing was we would set the next target dispatch. So we have a 5-minute dispatch. So the next dispatch used to be set based on the current output. So as you can see at 0, say 0, 0, the output was low, say around 10 megawatts, and then that used to be the target for the interval between, say, 0.5 to 10. But as you can see, and as is pretty common, wind is extremely variable. It can ramp up and down pretty fast. So when the time came to 0.00 or 0.5, the output was much higher, and then the target was much lower. So, and then the target got adjusted, but then the wind output came down. So it was very difficult to manage, even from a reliability standpoint, as well as the market. So what that does here with the DIR, as you can see, well, the left side is showing an unconstrained system, so it's pretty clear that the dispatch is following the actual wind output, which is following the target. But the beauty of that is when the system's congested, as you can see, the blue trace on top is the forecast. So that's what the wind resource, if it was not constrained, it can do. But based on the transmission constraint, the red trace is all that the transmission can accommodate. So then MISO, instead of sending it a target that matches the blue line, will send it a target that matches the red line. And then the actual output follows the dispatch target. So we have a very good handle. There is very little uncertainty. Sure, there are deviations as well, but that's true for any other generator as well. But majority of the time, majority of the megawatts that come from wind, we are able to dispatch pretty predictably. So in summary, wind, of course, it has created a lot of problems, but it has spurred a lot of development in our processes, in our market mechanisms, in our tools. And we continue to do this. The next, obviously, challenge is solar and then distributed resources. So we'll continue to do this going forward as well. And that's all I have. Thank you.